So we are back for this last session of the afternoon with Natasha Nadovesa. I'm sorry for the pronunciation.
It's Natasha,
I don't
but
know.
it's okay.
From ISCO.
Okay, thank you. So my name is Natasha. I'm a PhD student at ISMO with supervisors Daniel Pelaez and Fabian Gatti. And first of all, I would like to thank the organizers for the opportunity to present today. And as Daniel already mentioned in his talk, today I will go a bit more into details in work we have been done on development of CP-FBR method, which gives analytical representation of high-dimensional operators in canonical polyadic form. But before that, I would like to start with a bit of context. We are interested in studying reactive scattering of methane on nucleus surface because breakage of CH bond in this system is a rate limiting step for important industrial reaction, steam reforming, which is industrial way to produce hydrogen. And also it's a prototypical reaction of heterogeneous catalysis. There is a lot of experimental data on this system. So here is just one example that indicated that different vibrational states have different reactivity. And with that, that is to say that not all forms of energy are equivalent. Sorry. Okay. So I was saying, not all forms of energy are equivalent, and if energy is delivered to the system to specifically excite vibrational modes which are more reactive, we can achieve better reactivity even with smaller amount of energy compared to higher amount delivered in a wrong way. So now we want to have a theoretical approach to this system, but the one which would have comparable accuracy to experiments. That is, we want to include all quantum effects that may affect this process, such as tunneling effect for hydrogen and zero-point energy. And for that, we want to do full dimensional nuclear quantum dynamics. And in this case, full dimensional would mean 15 nuclear degrees of freedom. And if we talk about grid-based quantum dynamics, that would result in a very big grid, approximately 10 to the power of 15 grid points, but probably even more. So the approach we want, second note. Yes, thank you. So our method of choice for this is MCTDH, which is well known to be a very powerful method in such kind of calculations. And in here, wave function is expressed as a sum of products of time-dependent single particle functions. And since they are optimized during the propagation, much smaller number of them is needed to have already very good converged results. But to solve equations of motion, it's necessary to compute at each time step, at least formally, accurately multidimensional integrals. So to use this method efficiently, we need to have all operators expressed in a suitable sum of product form. Now for kinetic energy operator, it is usually not a problem because it's already prepared in appropriate form. In this case, for example, we have an operator which was provided by Fabian Gatti and David Lavergnan, which can be used directly in the calculation. But for potential energy surface, that is usually not the case. And even though they can be prepared directly in separable form, most often they are not. So in a subsequent step, we need to transform these potential energy surfaces into form that can be used. And now, as Daniel already talked about, there is a lot of methods which are available for that purpose. Starting with the oldest one, which is POTFIT, which is Tucker decomposition, and then all the further developments based on it. Most of them are grid-based, but there is also analytical form, so-called SOP FBR, which gives analytical analytical form of potential, which is in Tucker form. But for 15 dimensions and bigger systems, it's more suitable to use recently developed MCCPD, which is Monte Carlo canonical periodic decomposition. And if we compare expressions for those two, which is first one is Tucker form and CPD, we can see that what in Tucker form was expressed in a form of tensor, so-called core tensor, is here replaced only by a vector, which has R number of values. So as such, it's much more compact and more suitable for propagation. But when we do this decomposition, we have information on the grid which we actually used, which was our original tensor. And then if we want to change grid at some point, we need to do the composition again. And this is a scattering problem, because probably after we change initial conditions, we need to change a grid. And then to avoid to have to redo the composition every time, we wanted to now extend this SOP FBR, which is based on Tucker form, to CP FBR, which is basically the same idea, but now applied to canonical decomposition. So the main idea of the method is if we start with a function which depends on all the coordinates, and then we mapped it on the grid which we define, we form a tensor. And then after this tensor, after tensor decomposition, we obtain weights and factors, so factor matrices actually. And then instead of just storing those discrete values, we fit them. And we obtain this mathematical expression here, where we store a polynomial instead of storing just values on the grid. And then we can further interpolate it to any density which we need for our dynamics. So there are two main factors which affect quality of the fit. One of them is smoothness of factors, and the second is overfitting. Now about smoothness of factors, here I put two plots, which are, we have a decomposition for rank 15 and rank 30. Now again, this rank is actually number of terms in this expansion. So of course here nothing is visible, but this is just to show that we have discrete values on the grid points, which are expressed here on the x-axis. And this is for angular motion in water. Now we can, for better, to be more visual, we can express them as lines. And then we can see that for a smaller rank, they're smooth, but then if rank is increased, they're not smooth anymore. Now it's not that additional ones are not smooth, so that we can say, okay, we will just cut here and take just the smooth ones, but actually none of them is smooth. So we cannot, it will make fitting process much more difficult. And of course, if we increase this rank, we will make our, because the composed form is actually approximation of the original tensor. So as more we increase this rank, our approximation gets closer to original one, but then it affects the shape of our factors. So we need to find the balance between the two. And for overfitting, here in red is shown decrease of RMS as we increase order fitting polynomial on the coarse grid, but actually on the grid which was used for the composition. But in the green is RMS on the points in between. And that happens because if we increase a fitting polynomial, order fitting polynomial too much, we will represent those points perfectly, but then in between them, we will have behavior like this. So the process is, we define one grid for the composition, and then we store weights as such, under assumption that even when we increase density of our points, when we increase size of our tensor, those weights will still be fine as long as we keep the limits of our grid fixed, as long as we don't extrapolate. And we will see later that that is actually the case. And for the factors, we fit them, but we also take validation grid to control overfitting. This doesn't necessarily need to be a grid, but what is important here that for validation points, we use some points which are not part of the coarse grid, the grid of which we did the composition. And then we store fitting coefficients and weights as a CPFBR. Now we first tested it on a water molecule. Here is on the table is given the definition of grid. We have a coarse grid and a primitive grid. And then there is also shown Chebyshev order, which is order of fitting polynomial. In this expression, it will be this number of terms for every degree of freedom. And we tested it as a correlation plot. We represent energies from CPFBR and the reference energies, and we can see that they have good agreement in the whole energy region. And that is also the case for cumulative RMS. Here in black is original decomposition, and in red is CPFBR. They are represented perfectly. And then for interpolated grids, it's a bit higher, but it still has satisfactory value. We also use this CPFBR to find minimum of the function, to find the optimal geometry. And it compares well to the reference values, even though those points were not actually included in any grid which was used for preparation. And also we calculate vibrational states, and we compare them with references numerically exact pot fit. And here also we have a good agreement. Next, we went for HONO. The coordinates are defined as shown in this figure here, and they're actually taken from reference from which we also took surface. Now here, we introduced one more grid, but that was just for as additional test. So we defined the coarse grid, is shown here, on which we used for the composition. And then we used a slightly bigger grid just to make sure that those points will now be in between. Again, we don't need to use grid, but now it was simpler to use it as a grid. And then we have a primitive grid, which was done as a subsequent interpolation. And here we can see that in black is original decomposition, then in red is fitting on the coarse grid and the fitting on the fine grid. They have very good agreement. After interpolation, it's a bit higher RMS, but number of points in this grid is also much higher compared to the other two. And the correlation plot, again, we have good agreement in all range of energies. Now, for those two examples, we did the composition of the whole tensor, for which we used the Python library TensorLy. And in that case, this was when we define a tensor, the composition is performed taking into account all the points. But now for the next example, oh, sorry. First, this is still for HONO. We again did the optimization of the coordinates by fixing the torsion. And here we also were able to reproduce all three stationary points, trans, cis, and transition states compared to reference values. And vibrational states, again, compared to numerically exact pot fit, have good agreement. Now, as the last example, we did methane molecule, but now we consider the molecule as methane as isolated molecule far away from the surface. So we have 9-dimensional potential. And here is how we define coordinates for this. They're also taken from the reference. And also a definition of grids is given in the table. Now, as I was saying, for methane, in the coarse grid forms two big tensor, which cannot be done anymore with this library, which takes into account entire tensor. So for that, we use now MCCPD, which is doing the composition based on sampled points of our surface, and then we can sample only, let's say, in this case, we are interested in lower energy regions. So here on this graph is shown energy distribution of points which we took. Here is a number of points, and here are energies. In the black are expressed sampling points which we use for the composition. The red are points that we used for as reference for fitting, and in green is validation for fitting. And the number of points that we use for each of the stage is shown here. And then we also sampled some more points at the same energy distribution as we use for in the preparation of CPFBR, just to serve as a test to test quality of our analytical form in all three grids. And here we have on the correlation plot, we see that agreement of CPFBR, this is for primitive grid. Agreement of CPFBR is good with compared to the reference in region which we are interested in, of course, and then in higher energy regions, that's not the case so much, but also we didn't actually use data from these higher energy regions in any step. And that can also be seen on plots where are cumulative RMS. Here also in black is MCCPD decomposition on coarse grid, and in red is CPFBR on coarse grid, and then in green is CPFBR on validation points, and in blue is on primitive grid. And also there is in purple, we did the MCCPD directly on the primitive grid. So again, on the region of interest, they all have a good agreement. And then we also computed the vibrational eigenstates using CPFBR and compared it to MCCPD, performed directly on primitive grid, and with reference values where they used original surface without any kind of transformation. And here as well, they are all in good agreement. Now also, we should mention that time to prepare CPFBR is actually lower than MCCPD. So for CPFBR, we did the composition on the coarse grid, then fitting, and then interpolation. But for MCCPD, we did then directly the composition on primitive grid. But of course, this difference is not significant, but we expect it to scale with dimensionality. But also, actually, the main added value of CPFBR is that we don't need to repeat the composition if we would need to change the grid, while for MCCPD, we would need to repeat to do it again. And now just to summarize, the analytical CPFBR surface gives results which are as accurate as MCCPD, but requires much smaller number of past evaluations. And it should be able to deal with any system within the reach of MCCPD, since we use MCCPD now as initial step to do initial decomposition. And it enables further interpolation to grid of any density without need to repeat the decomposition. But it's also important to mention that this so far was only about bound systems. Now for unbound systems, it's a bit more difficult and it's a bit different process. That's what we are doing at the moment. We're trying to prepare CPFBR for our full system, meeting an equal surface, which will then be used for calculation of quantum dynamical calculation of mode-specific reactivity, which I mentioned in the beginning. And finally, I would like to thank my supervisors and the other members of our group, as well as our collaborators. And of course, thank you for your attention.
Two questions. One, when you did the test on the HONO, you mentioned as a reference you use the fit potential of HONO, but I guess you don't need that, so because it's already as a sum of product, this potential. So if I remember well.
Well, we did actually pot fit for HONO.
You did pot fit, okay.
Yes.
Okay. And my second question is, at the end, you show when you were doing this CPFBR, can you do, or someone can do the same thing, but with, I don't know, the acronym, the MCPD with FBR. Is it possible? So that you can extend it more easily without reduce the fitting in Monte Carlo things. Yeah, with FBR at the end. Yeah. Yeah, no, but the fact that in the usual MCPD, it's too complicated. You mentioned that you have to reduce all the things if we change the grid. But so if you do the same trick as you did to transform to FBR, you would not need that. But when you do the FBR, one advantage is that you don't need to recompute all the potential, let's say, on a new grid, because it's on the basis. So can you do also the same thing also in Monte Carlo things, with exactly what you have done?
That's kind of what we did, because we did the composition with MCCPD and then just fitting. So I don't know what exactly you mean to transform it to.
I don't know.
I don't know if there is some other way.
I thought there was the other difference between the two.
No, there actually is the whole point is that you want to get a specific form. That's why it turns out to be very compact.
Okay.
It's very dangerous. It's mathematical. For that, it's a nightmare. It's not like you're going to start and say, I've got this form. It doesn't work like that. So you need a seed. This seed is provided by any physical composition. It's that. would be a matter of saying, okay, we have to, so there's something we haven't done yet, and there was a question that for us. So we could write some equations so that we could do ourselves directly the optimization directly.
FBR. Yeah, I
We
think.
haven't done that.
Okay.
So the equations are written, we have to implement them and so on, but we have to this working. So for the sake of PhDs, it's also.
Yeah, fine. Okay, thanks.
Other questions? No? Okay, so thank you again. And now we are going to listen to Guillaume Domp with a remote speaker. So